A conveyor belt accelerates to 3 meters per second, carrying thousands of ripe, sun-ripened tomatoes toward a high-speed packing zone. In traditional factories, mechanical steel fingers slam shut with rigid precision. But when steel meets fresh fruit, the result is instant crushing, bruised skin, and thousands of dollars in ruined product. The fundamental bottleneck of automated food processing has always been the sheer fragility of organic matter. For decades, standard factory automation relied on hard metal claws designed for forged auto parts and plastic housings. These rigid tools apply fixed force vectors that work brilliantly on uniform engine blocks. Yet an apple, a bakery pastry, or a skinless chicken breast resists uniform geometric rules. When a rigid jaw attempts to seize an irregular object, pressure points concentrate on tiny areas, tearing tissue and destroying shelf value in milliseconds. This physical mismatch created a massive wall for logistics engineers. While car assembly lines moved to total mechanical independence, food packaging remained heavily reliant on human hands. Human fingers possess an incredible natural compliance, adjusting instantly to the soft, slippery, and uneven surfaces of fresh produce. Replacing that gentle human touch with heavy motorized iron proved almost impossible, forcing processing plants to keep thousands of workers on cold, repetitive manual packing lines. The breakthrough came not from building harder machines, but from softening the contact surface through soft robotics. Engineers abandoned rigid linkages and turned to flexible elastomer structures designed to yield upon contact. Instead of fighting the soft nature of organic items, new systems matched the mechanical impedance of the food itself. This design shift laid the foundation for a completely new class of flexible end-of-arm tooling. At the heart of this physical shift are specialized silicone grippers designed with hollow inner chambers. When compressed air flows into these internal channels, the elastic material expands unevenly across its structural geometry. The outer wall stretches while the inner surface remains constrained, causing the soft finger to curve inward like a human digit. Through simple air pressure, the actuator wraps smoothly around delicate produce without requiring complex motor gears. These custom pneumatic actuators operate through precise pressure regulation rather than motorized positional feedback. When air rushes into the hollow core, the silicone fingers deform safely around whatever shape lies beneath them. Because the expansion is driven by fluid pressure, the contact force automatically spreads evenly across the entire surface of the fruit. This natural enveloping action eliminates pressure hotspots, stopping bruised flesh before it ever starts. Older robotic systems relied on high-resolution cameras and expensive software to calculate exact grip points for every single item on a belt. If a peach was rotated slightly, the computer spent precious processing cycles remapping finger trajectories. Soft pneumatic tools eliminate that computational load entirely through mechanical compliance. The physical flexibility of the material absorbs the spatial variance, letting the tool conform to the object without waiting for computer recalculations. Down on the main packaging line, this structural softness translates to blinding mechanical speed. High-speed Delta robots mounted above processing lines drop down in fractions of a second, slapping silicone fingers around fragile baked goods and lifting them effortlessly. The air pressure flips from positive to negative in milliseconds, releasing the item into retail trays without leaving a single impression mark. Line throughput suddenly leaps from dozens of units per minute to hundreds. The harsh realities of the food processing floor demand hardware that survives relentless washdowns and chemical sanitizers. Traditional metal joints with open gears collect organic debris and require constant grease, creating major contamination hazards. In contrast, smooth silicone grippers present seamless, non-porous outer surfaces that resist bacterial buildup. Plant crews spray down the entire arm with aggressive caustic cleansers without risking mechanical corrosion or fluid leaks. Inside the material science laboratory, the formulation of these elastomer compounds determines their operational lifespan. Engineers blend specific grades of silicone to achieve exact tensile strength, tear resistance, and flex memory. A single soft gripper finger must flex millions of times under high pneumatic pressure without developing micro tears or permanent deformation. Chemical additives also ensure the silicone maintains its flexibility across extreme thermal spectrums without leaching into edible products. When mounted on 3-axis delta robots, these lightweight tools reduce total payload weight at the end of the arm. Lower mass allows the robotic motors to accelerate faster, execute sharper changes in direction, and reduce mechanical wear on the primary drives. The combination of lightweight air-driven fingers and high-speed overhead kinematics enables uninterrupted operations that run 24 hours a day with minimal mechanical degradation. From an economic standpoint, the deployment of soft grippers transforms factory margins. Food spoilage during packaging drops significantly, recovering lost profits that used to rot in waste bins. Plant operators report immediate reductions in raw material damage, while line speeds double without requiring larger floor footprints. The lowered reject rate directly improves net yield across high-volume agricultural operations. Consider the complex challenge of handling raw poultry cutlets or delicate seafood fillets. These items are slick, non-rigid, and highly variable in thickness, making them a nightmare for conventional suction cups or rigid jaws. Soft pneumatic fingers wrap under the soft tissue, creating a broad cradle that lifts the wet item through surface friction rather than pinching force. The item moves safely without tearing delicate muscle fibers. This technological shift changes the daily lives of factory line personnel. In legacy facilities, human workers suffered high rates of repetitive strain injuries from standing along freezing conveyor belts for 8 hours, manually turning and packing fragile produce. As soft automation handles the high-frequency physical grasping, human operators shift toward managing system logistics, monitoring quality control, and maintaining pneumatic fluid lines in safer, less physically punishing positions. Operating inside sub-zero chillers presents severe challenges for standard robotic hardware, as cold turns rubber brittle and freezes hydraulic lubricants. Modern soft pneumatic systems use specialized cold-resistant polymers and dry air lines that maintain flexibility down to freezing temperatures. Whether picking frozen berry packs or ice-chilled salmon, the air-driven fingers retain their soft compliance, protecting structural integrity where hard plastics shatter. The systemic benefits cascade outward through the regional food supply chain. Faster, gentler handling in the packing house extends overall product shelf life by preserving the natural protective skin and bloom of fresh fruits. Berries packed without skin micropunctures resist mold growth days longer during transit, reducing retail-level discard rates and improving fresh produce availability across distant municipal markets. Integration with modern factory control networks links soft grippers directly to real-time weight sensors and optical sorters. As items move down the line, automated valves adjust pneumatic supply pressures on the fly. A lighter, softer, ripe avocado receives a lower pressure air pulse, while a firmer, heavier item gets slightly higher actuation pressure. This dynamic force adjustment optimizes grip security while eliminating all risk of physical damage. Engineers continuously stress test these pneumatic components to push durability limits. Custom rigs flex silicone fingers through tens of millions of continuous pressure cycles inside sealed environmental chambers, measuring pneumatic leakage and material fatigue. By mapping the precise failure points of elastomer chambers, manufacturers build quick-change modular manifolds that allow technicians to swap out worn silicone fingers in seconds during routine downtime. The lower capital cost of soft pneumatic tools speeds up market adoption across mid-sized regional packing plants. Unlike multi-axis electromechanical claws with complex internal servo motors, soft pneumatic grippers rely on simple directional valves and off-the-shelf air compressors. This low mechanical complexity drastically reduces upfront installation expenses, letting food producers recoup their automation investment within months rather than years. Across global agricultural processing, soft robotic handling unlocks scalable automation for harvests that were previously untouched by machinery. Delicate crops like strawberries, fresh figs, and soft cheeses can now transition directly from field bins into consumer clamshell packages without human contact. This scaling capability bridges critical labor shortages during peak seasonal harvests, stabilizing the flow of fresh food from farms to city centers. Beyond the food industry, the foundational principles of soft pneumatic actuation are reshaping medical devices, logistics sorting, and fragile electronics manufacturing. The ability to manipulate fragile, irregularly shaped objects using pure air pressure and passive structural compliance offers a universal solution to physical handling challenges. Soft robotics demonstrates that mechanical strength is often inferior to intelligent material flexibility. Ultimately, the transformation of food packaging through soft pneumatic grippers proves that solving industrial friction requires rethinking mechanical force from the ground up. By swapping unyielding steel for flexible silicone and dynamic air pressure, engineers have built a bridge between cold industrial automation and the delicate complexity of organic nature. The result is a faster, cleaner, and far more resilient global food supply chain.